Did you hit record? Okay, I'll begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. We just pray that you would help us to solve lots of problems today and to gain understanding, Lord. In your name I pray. Amen. Let me start with one that was asked me earlier. This one, integral from 1 to infinity of dx over e to the x plus x. So I was like, this is by comparison. This problem you're supposed to do by the comparison theorem, which he relegates to exercises. Not happy about that. Which one was this, Josh? Number?
This was question, this was earlier on.
Yeah.
I think I did this one as well.
8.8, number 62, I think.
Yeah.
So earlier, I had told you, Josh, that 1 over e to the x plus x was less than 1 over x, and it was greater than 1 over 2 e to the x. And I told you that this was like useless because the reason this is useless is because, of course, 1 to infinity dx over 2 e to the x converges. And I also know that the integral from 1 to infinity of dx over x diverges. So I was like, I was despairing earlier because, I mean, I also explained to you, Josh, that this f of x was positive, it was positive, it was continuous, it was decreasing. We argued all those things, right? And yet that was no help to me because like the things I could think of were either something that's larger and diverges or something smaller and converges. So those don't tell me anything. And I told you that I was being dumb and that there was something really, really obvious that I was missing. And I stand by my statement because what I should have done is just tell you this. E to the x plus x is less than what? What could I put here that has a 1 over e to the x, right? Exactly. This has an integral which converges. It's bigger than that. So by the comparison theorem, this must converge as well. See, because the integral from 1 to infinity of dx over, see, it's like, what's wrong with me? I don't know why I couldn't think of this earlier, Josh. I mean, just sad. But so this integral we can do, right? Limit t goes to infinity. Minus e to the minus x evaluated from 1 to t, which is the limit as t goes to infinity of minus e to the minus t plus e to the minus 1, right? So in fact, this converges to 1 over e because that piece goes to 0. So you can see that that integral converges. It's an integral of a function which is larger than the given integral's integrand. So by comparison, it must also converge. So, but comparison, this is the main thing in your way of using comparison test effectively, is having the insight to like write down which function's bigger or smaller as appropriate, Yep. 9.5, number 26. Sounds like a possibility. So we're supposed to determine convergence or divergence of the series. Number 26, so we got sum n equals 1 to infinity of 2 times minus 1 to the n plus 1 over e to the n plus e to the minus n. So he's told you that's, and he gave you a formula in terms of a hyperbolic secant. Well, that's lovely. Who cares? Sorry.
I didn't even see that. I did not see that.
Yeah. I mean, sure. I mean, this. If you want a formula, this is the sum. I don't think this really even matters, but I mean, it's true. That's Kosh of n. So but whatever. Anyway, the point is that we have b sub n is equal to 2 over e to the n plus e to the minus n, right? And this is it's an alternating series. So identify Bn and S is alternating series, right? So we can use the alternating series test. This was what, section 9.5, number 26? Okay. So what does alternating series test require? We need the limit of this thing, right? What should it go to? Yeah, it has to go to 0, right? And what else do we need? We need that the b sub n's are positive and right, the b sub n's have to be decreasing. Yeah. So I think we got limit 0 here. I mean, it's actually pretty clear. This piece, what happens here? We've got this going to 0. This piece goes to infinity, right? So this integral's type 2 over infinity, essentially. The point is, after a while, the e to the n wins, and we have something very large in the denominator. So this is 0. So I don't think further work is really required. But we should explain why it's decreasing, right? And perhaps there, okay, so there's where his comment is a little bit helpful. I'm going to stick with Bn equals to 1 over cosh n. Right? So note that if we have f of x equal to 1 over cosh x, it has f of n equal to b sub n, right, for all n. So if the function is decreasing, then the sequence b sub n is also decreasing, right? What's the derivative of this function? Minus, yeah, how about quotient rule? Minus sinh x over, or if you like, the chain rule. So there you go, that's the derivative of f. Now we're looking at n whole numbers, right? So what's the sinh for like positive numbers? Sinh is positive for positive inputs. And cosh squared is always positive. So this is clearly less than 0. For x greater than 0, actually. Which then tells me that b sub n decreases. Because this tells me that f is decreasing. All right, so if you find a function which is matching a sequence, right, if the matching function is decreasing, the sequence which it extends is likewise decreasing. Yeah.
In order to prove that it's decreasing, could you just plug in like 5 points and see those 5?
No, I mean that's a start, but that's not a proof. I mean, I would give significant partial credit for that, but I think that's more work too. Yeah. I mean, that would eat up a lot of calculator time to actually plug in 5 choices of n, you know. Anyway, let's see here. That's the quickest way I know to show that it's decreasing, like carefully. And I think that's the reason that he has the formula hyperbolic secant n in that problem. Yeah. Nope. Oh, we're not done yet, though. So now we've shown it's decreasing. We've shown it's limit 0. It's positive. What's left? Therefore, S converges by the alternating series test. Sorry, I just had to get my system. What was your question?
Never mind.
Okay. So that's
Yeah.
good. Yeah.
I just did, I got all that, but I just was proving it.
I mean, to be entirely honest, I mean, we're talking about, like, this is a problem on a test, right? Maybe it's worth 10 points, right? If you've told me it's an alternating series and the terms limit to 0, and you state that the terms are decreasing, and you're not wrong, then I'm probably not going to take off much, if anything, for not proving that they're not decreasing. Like, we're majoring in the minors here. I mean, this is a small chink in the armor of your argument, not having that there. Yeah.
Wait, so the first derivative test to prove that it's decreasing, that's not like enough proof? Oh, okay.
I'm saying, suppose that wasn't there, yeah. Suppose you just said, it's clear these are decreasing, because I looked at the first three. You know, I'd probably take off like 10% credit from that problem. Mm-hmm.
Another question. Remember,
Mine is like a general question, so.
okay,
Okay, so I had a question about tests for the direct comparison test. Like, let's
Mhm.
say you have like I understand how that works, but for the limit comparison test, if you're subtracting in the denominator, but it's still like similar, is that when you use it? Because like, is that?
It depends on whether you're aiming for divergence or convergence of the series. If we're aiming for divergence, then minus isn't bad for direct comparison, because we can drop the thing that we're subtracting if it's positive. So we can find something smaller that diverges. But if we're aiming for convergence, then when you've got something like 1 over something minus something, then yeah, our usual move is to just replace, you know, right? I mean, that's kind of our typical go-to move. And so if I've got a minus there, that spoils it, yeah, and then limit comparison's probably the right tool.
Then I use limit comparison.
Limit comparison has its, you know, it has its place. It is for terms with positive, series with positive terms, right? There are other places where I got to use ratio test or something else, you know. Yeah. Mm-hmm.
Remember last time when we did like the convergence divergence thing, like if A sub n was convergent and B sub n was divergent, like what would it be? There's another one. Remember I was talking about the conversion Nash? It was yeah. If they both converge and you multiply them,
Yeah.
like you have to prove that. But it's like it makes sense in my head, but I don't know how you have to prove everything with math. I don't know. It's just,
There's a problem about the product of series.
it's 9.4.
Uh-huh. Let's see here, 9.455. So you're given, you've got AN, you've got BN, right? And then they're both given to converge.
Yeah.
Anything more? They're non-negative. Yeah. Supposed to show the sum A and Bn likewise converges. Okay, so that's actually, now when I think of the product of two series, that's actually something different. This is the term-wise product. There's also, like, this is something different, A1 plus A2. See, if I just say the product of two series, usually people are thinking about that. And that's a little bit, that's actually considerably more subtle than this problem. So let me focus on the problem that is. See, that's not, those are some of the terms which are in here. Like when you multiply this out, you've got A1, B1, right? And you've got A2 and B2. So you've got everything that's in there, but you got other stuff in here. Like there's also A1, B2, and A2, B1, etc. There's tons more terms in this than there are in that. Anyway, let's focus on your problem. I was saying later we're interested in this for other reasons. We haven't talked about that yet? Did we not? Nah, whatever. All right, so how would we, it says we're supposed to prove that, huh? Yeah, okay, here's the proof. One of you guys told me limit comparison, thank you, that was great. That makes it easy. So an, bn is greater than 0, right? So use limit comparison test of s, let me call this thing s, to, you pick it, I mean, you can't go wrong here, let's say a sub n, which is given to converge, right? What does limit comparison look like? Oh, I see the problem. That's actually maybe not as helpful as I thought it was. So that's an bn over an, oopsie. I mean, that's great. That's bn, right? But what does that go to? By nth term test, this is a convergent series. I know this goes to 0. Does that even help me? When does limit comparison apply? When does limit comparison tell us something useful? Well, it connects the fate of the series and the compared series, provided that the limit of the quotient's what? Greater than 0 and a real number. Right. See, where is that silly thing stated? It's in the it's in limit comparison. So this is theorem 9.13. If it's finite and positive, yeah. So this is unfortunately not the case. So limit comparison doesn't help us, does it?
Directly compare one of the convergent series and compare that to the product. So define another series as you did with HUs and then directly compare.
You want to compare?
Because B sub n is bigger than 0, but it's less than A sub n, B sub n.
All right, so this didn't work. Let's try something else. So you guys said you want to say A sub n is less, I don't know if A sub n is less than B sub n.
But A sub n should be less than A sub n times B sub n because they're positive, right?
Why, you said A sub n,
It's less than A sub n times B sub n. And then A sub n
because they're both,
and then A sub n is bigger than 0.
whoa, flag on the play. Wait.
DCT.
Wait. Bn equal to half. This is possible. I didn't say that Bn was greater than 1. Heck, if Bn is always greater than 1, we're out of luck anyway. That's going to diverge. It's certainly not going to converge to 0. So I think this, to quote my community college professor, this dog is not going to hunt. Yeah, I mean, a noble goal. I'm not saying I got a better idea at the moment. Any other ideas? This is an odd problem. Is there a hint?
It says n equals 1. I don't know if that helps.
It says n equals 1.
Yeah. Yeah, so if n equals 1 as a person infinity, why can't we use DCT then? Because that's...
There's something lost in translation from here.
Wait, so if we know that both of those series converge, then we know that the limit as n goes to infinity of each of those series is 0. That's the unidirectional path of the nth term test. So we know that that limits to 0. So then, yes, but then what am I going to do with that?
Unfortunately, knowing that the product of them goes to 0 shows that it might converge, but it
Yes,
does not
yes,
show us
yes.
that it does converge.
Yeah, I wasn't trying to go there.
Ah.
Won't that work though? DCT stuff?
50. Stupid book.
Oh, yeah, it just says proof.
Proof. Sorry, I don't know why he's even looking.
Because like the summation.
There are no solutions, there are only answers, right?
N equals 1 to infinity for both of them. So can't you assume that n will be greater than 1? Therefore, you can do that DCT.
Direct comparison to what? I mean,
What we had earlier, we said if b sub n was 1/2, then it wouldn't work. But if it's greater than 1,
well,
because if they're both greater than 1, then multiply them maybe back here. You feel me?
but we're trying to prove that it converges, so we're not, I mean, I don't, yeah.
Like, just like in terms of like a property, if those two are given to converge, right?
Yes.
So if they converge to some constant, then it's just multiplying two constants, essentially, isn't it? So by the definition of like convergence, it converges to some constant. So it has to converge to a constant because the product of two real numbers isn't going to be. Can't you make that argument?
So it makes sense in my head.
I don't see how, I'm not understanding how that tells me anything about this. I mean, it's true that this is something, and this is something, and that these are real numbers, right?
Yeah.
And it's also true that if I multiply these, I get AB, but that's really not making any kind of progress on this. What I would need to do, short of another idea, when does the ratio test, perhaps? Do we have ratio? This is 9. I know that's in the next section, but wait.
2 sections beyond.
Oh, we're beyond that? Where's this from?
So we just had LCT, DCT.
Yeah, but I don't care. I don't care. Let's think about ratio test. What does ratio test say? It says that it converges absolutely. We just need the absolute value of a sub n plus 1 over, I'm trying to think of how that goes. Oh, that doesn't help me. Or does it? Or does it? If I think of this as being Cn equal an Bn, right, and I apply ratio test, I think that actually might do it. Ratio test, Cn plus 1 over, oh, I see problem. Oh, maybe I don't. This would be an plus 1, bn plus 1 over an times bn, right? Which, these are positive series, so I can drop the absolute values, they're positive, right? A positive series, a positive convergent series is automatically absolutely convergent, by the way. And so because the series A sub n is given to me to converge, I know that this converges to something, let's say L1, and this converges to L2, where L1 and L2 are both less than 1, right? So this converges to L1, L2, which is less than 1 as n goes to infinity. So therefore, by the ratio test, that's convergent. That's one way to do it. That's probably not what's intended here. There should be some kind of sneaky way of writing the nth partial sum like this. Well, there's probably some kind of sneaky way of rewriting that by adding 0. If we were to add 0 in a sneaky way, maybe we could convert that into things we know that converge. Do you have any ideas? What if I replace this with like, there's no infinity here, n. If I do, say, a sub j minus a plus a, b sub j, perhaps, then I would have oh, I think that does it. Look, I know A exists, right? I know as n goes to infinity, the nth partial sum of the A series goes to that, right? So the reason that gave me hope that if I add and subtract A here, that will allow me some kind of entanglement of these results, so to speak. So a sub j minus a times b sub j, this is one thing, right? On the other hand, over here I have this a times bj, right? What happens as n goes to infinity of this? As n goes to infinity, we get this goes to 0 as n goes to infinity by the nth term test, right? And this just becomes minus a times the sum j equals 1 to infinity, 1 to n of b sub j. And then this becomes what? Plus. Well, there's something wrong with my argument. Yeah, so I'm cheating. There's something cheating about what I'm doing because it's not quite honest. The nth partial sum doesn't have to go to 0, but my argument is saying it's 0. This thing I did with assuming this goes to 0, that's in the limit. Yeah. Right, why isn't, I mean, but here I'm not. That's the thing is this goes to 0, but there are also infinitely many of them, and I'm not really being honest with you guys when I do that. Yeah. So, sorry, this is... Let me stop talking about this problem. I found you one good solution, even though it's from 2 sections ahead. So, other questions, please, please, please.
9.5, number 18.
9.5, number 18. Ah, this one's not bad. Oh, this one ain't bad. So the thing you got to realize here is that this is really, this is -1 to the -1 to the n.
That was pretty sneaky. We talked about this in class, I think, once.
I have talked about this in class. That is true. So here, yeah.
Why isn't that equals 1? Because wouldn't cosine be positive and pi? No, it's not. It's negative.
Cosine pi is -1. Cosine 2 pi is 1. -1 squared. Cosine 3 pi. -1. So let's get this one. So this is an alternating series. We have b sub n equals to 1 over n. This is decreasing. It's positive, right? And surely b sub n goes to 0 as n goes to infinity, right? Decreasing, why? Because 1 over n plus 1 is less than 1 over n, right? It's positive because 1 over n is greater than 0, right? The thing is, this is the limit as n goes to infinity, 1 over n equals to 0. I'm most likely to take off points in terms of, like, when you just say bn goes to 0 if it's not obvious. If it's something that's actually indeterminate and requires an application of L'Hopital's rule or something, I probably want to see it, you know? If it's something as simple as this, if you just say that bn limits to 0, I'm probably fine with it. I mean, I'm not asking you to show work here. I just want you to say it. Anyway, so it's decreasing. It's positive. It limits 0. It's an alternating series. Therefore, S converges by the alternating series test.
Does it conditionally converge?
Yes. Because the absolute value of this series is the harmonic series, the p equals 1 series, which is divergent. Yeah. Next question.
Could you see 9.5 number 80?
9.5 number 80.
That's not too high.
It's possible. I can try.
It's a review question.
Yeah, it doesn't. Yeah, it looks harmless enough. We have log n over n. Log n over n equals 2 to infinity. This is number 80, section 9.5. It's a review question, which means not by the methods of this section, essentially. So let's see here. I don't think the nth term test is helpful because that does limit to 0, right? Direct comparison with what? 1 over n. Well, that's either going to give you a log n or a 1 over log n, which either is going to go to infinity or 0. So direct comparison with 1 over n isn't going to help me because the limit comparison is not going to apply when you actually calculate it. I believe, what's that?
We can't do limit comparison, we can do direct comparison.
Oh, direct comparison. Did you say direct comparison?
It's a direct comparison.
Oh, I'm sorry. I'm an idiot. Am I?
I just like direct comparison. It's the only thing that makes sense to me right now.
Let's see here. This is greater than or equal to 1 over n, right? Is that true?
No.
Well, maybe. I got to think about that for a second here. This is the natural log of 1 is 0, right? What's the natural log of 2? So, I mean, yeah. Now, on the other hand, if you get to 3, right, natural log of 3, well, in between those 2 points, we got the natural log of e, which is 1, right? So this is true for n greater than or equal to 3. But you know what? That's enough. We can do direct comparison on the tail of the series. We don't really care if the first term violates the inequality. Just so long as it happens for n sufficiently large, we're good. And so, yeah, that does it, because, of course, the integral, well, excuse me, integral, listen to me, series, you know, n equals 3 to infinity, 1 over n diverges, which implies that the series n equals 3 to infinity of log n over n diverges, yeah. Alternatively, you could calculate the integral of natural log x dx over x from 2 to infinity and show that that diverges. See, that's the integral of, well, let me do it over here. Integral log x dx over x is what? It's u du. And so that's 1/2 u squared plus a constant. So this is really limit as t goes to infinity of 1/2 natural log of t squared minus 1/2 the natural log of 2 squared. And that works out to infinity. So by the integral test, you could also show that it diverges.
So that proof will work even though the series is from 3 to infinity instead of the original 2.
Right, because if this diverges, that of course implies that that diverges. Yeah. Mm-hmm.
That first term diverges because it starts at 3, right? Because wouldn't that normally converge to 0 if it was 0?
Both of those expressions go to 0, but that doesn't, I mean, the question is the corresponding series, right?
But if they both go to 0, then how are they diverging?
The series corresponding to those terms diverge. Those terms themselves converge to 0. Although it's not immediately obvious that log n over n converges to 0. That's, I'm doing a L'Hopital's rule I didn't write down. I mean, it's originally type infinity over infinity, but the fact that those terms go to 0 doesn't mean that the series are convergent. Corresponding series are divergent, in fact. Yeah.
So, like, we could have just done this out of the gate with the integral test?
Yes. I think this is an integral test problem. Yeah. But you can go either way. I mean, there's usually 5 different ways to do most of these problems. Yeah.
Well, the problem I'm asking is like similar to this one, but the bottom just like n to the p, and I didn't know.
Yeah, that's going to be about, it's a couple of pages of work. There's cases you got to consider. There's lots there. That problem is as hard as proving the p-series test, because you have to think about different cases. I think we talked about that over on that board once upon a time. It's the thing is this problem. P is a variable. Is it 1 or 2? 2 to infinity? Yeah. So this problem here, for different choices of P, different arguments apply. Like I think, if you look at f of x equals log x over x to the power p, and you look at df dx, what do you get? Right, so you get, multiplying by x, you get 1 minus p x to the p log x over, x to the 2p plus 1, I suppose. When is this, the question is, when is this less than 0, right? For x greater than 1. I mean, that 2. When that condition's met, I've got a continuous decreasing positive function. So, sorry, positive function. Oh, no, it's positive. Never mind. Log 2 is fine. It's the inequality was monkeying. Log 2 is positive. It's fine. Nonsense. But you see, that's only going to be true for certain p, that this is actually positive for all, if yeah.
You did the quotient rule to take that derivative.
Not negative, I mean. What's that? Yeah.
I said you used the quotient rule to take that derivative, right?
Yeah.
When you have to multiply that first term by x to the p, or did you?
Oh, yes. Thank you. That's helpful. You're right. In fact, that makes this, because it's starting to weird me out, what I was about to say. Thank you. That's much better. Oh, yes, much better. So we actually get x to the p times 1 minus p log x. Yay. Divided by x to the 2p plus 1. I need this to be less than 0 in order for f of x to be decreasing, which really means that I need 1 minus p log x to be less than 0 to make it decreasing, which means I need, minus p log x to be less than minus 1. Or let's write this like civilized human beings. This is 1, well, what is that? That's p log x greater than 1, right? Multiply by minus 1, flip the inequality. The question is what p it makes this so. Well, this, I mean, what's log x look like? Like this, right? And we're looking for basically beyond here, right? X greater than or equal to 2. How can I have this inequality be true? What do I need p?
That LM2 is 0.692.
Yeah.
1 divided by that. And then
Well, what I'm thinking is as long as p is positive, log x will get big enough eventually to make this true. And I mean, as long as I can show that the integral eventually goes to, is eventually converging, then I can throw out the terms before that point and still use a test or whatever. But so, oh, fine. I guess we could say that's log of x to the p, right? I don't know. I think p greater than 0, we can make an argument that says it still works, but certainly for p less than 0, we're in trouble. But if p is less than 0, then other arguments take over. I was trying not to get back into all this again. That problem is involved. There's a lot of cases. The integral test takes care of a lot of them if you work it out carefully, but not all of them. There's sometimes you can use the nth term test for a bunch of the other cases. Yeah. So I think that's what we figured out before, is where the integral test stops applying, the nth term test takes over. Why is it so hot in here? Is it just me? Am I imagining it? Grief. Someone asked me an easier question to make me feel better about my day. In the homework, though. In the homework. Yes, sir. 9.6 number what? 18. Yes, we have not done nearly enough ratio tests, have we? Here we have n times 7/8 to the n. N times 7/8 to the n. N times 7/8 to the n. Sum n equals 1 to infinity All right. It's number 18 of section 9.7, is it? Or 6? 9.6. Yeah, we're not to 9.7 yet, are we? Okay. All right, so we're probably supposed to think of the ratio test here. Call this thing AN, right? So I should look at AN plus 1 over AN. And, I mean, technically the absolute value of that, of course, but that's kind of silly here because AN is pretty clearly positive, you know? So that's going to be N plus 1 times 7/8 to the N plus 1 power, right? Then I multiply by the reciprocal. And what's that reciprocal look like? It looks like N downstairs. Oops. The reciprocal is 1 over N times 8/7 to the N. Does that make sense? And then we just, collect stuff and do algebra. N plus 1 over N. And then I've got 7 to the N plus 1 minus N. I've got 8 to the, looks like minus N minus 1 plus N. I mean, however you guys want to organize the algebra, it's up to you, but after the dust settles, you ought to get 7 over 8 that remains. I don't like the way I wrote the algebra down just now. I'm going to do over. It wasn't wrong, you can leave it. It's fine. But I'm going to try a different format for you guys. 7/8 to the N plus 1. You just got to be careful to make your fractions big enough, yeah? But sometimes I don't like this. I mean, sometimes I like to multiply the reciprocal. But this one, I think it's just maybe better to do this. So that's N plus 1 over N. And clearly 7/8, yeah? What happens as N goes to infinity then? Oh, that was dumb. This is what? This is 1 plus 1 over N, right? Times 7/8. So what happens? This goes to 7/8, right? Which is less than 1. Thus, S converges absolutely by ratio test. Yep.
That kind of, when you have equals N plus 1 over N multiplied by 7/8, that kind of looks like, why not rewrite that as a sequence of partials, or of the partial sum things? Can you do that or no? Can you rewrite that as a sequence of partial sum? Or I'm sorry, as partial fractions?
Partial fractions. I don't see that here.
I'm confused.
So the ratio test, again, what we do is we take the ratio of successive elements, successive terms in the series, and if you can show the limit of that works out to something that's less than 1, then you get absolute convergence. If the limit works out to something greater than 1, you get divergence. If it works out to 1, you get nothing. So, yes. That's also page, just a reminder, guys, if you want to, what's a nice way to study for the math battle tomorrow? Well, I mean, be here, right? But this page 632, it's got most everything in right there. So 632. Yes. So tomorrow, what were the rules for math battle? Lest I forget. Open notes, closed book, right? Yeah. you printed out handout from the website, that's okay. It's just, the actual text I would not want to be out is all. So, well guys, I think class was over 3 minutes ago, I'm sorry. Yeah, just press it again, did you get it?